This section on DMET Console software is about reviewing genotype results with a focus on sample and marker summary statistics, creating and using a custom marker list, and concordance check. When genotyping has completed, a list of all the genotype results for that particular data set will open up in a tabular form. It's the CHIP summary table. If you don't see this window, or if you want to open up results later, you can right-click on a particular data set in the genotype results group and show the CHIP summary table, and that will open up the same table. Let's look at the table in more detail. And let's hide this lower window. Okay, so each row refers to a particular sample file. Two of the sample files were processed earlier in the day than the rest of them. Batch name is only filled in if you do dynamic genotyping. If you use fixed method, this will be blank. In bounds, this will tell you whether the sample has failed or passed QC based on some metrics. The metrics that show failures show up with these red dark backgrounds. So there's two samples here that are considered out of bounds because of a failure in a metric called the QC call rate. The metrics to decide whether a sample is in bounds or out of bounds can be configured in this QC thresholds item. You can see that for the DMET Plus array, the thresholds that are used to decide whether a sample is in bounds is that the QC call rate needs to be greater than or equal to 98, and that the sample type is not equal to plasmid. You could, for example, make your pass-fail criteria more stringent to take 98% to 99.5%. If you are changing it, you'll get a notice that you're saying you're using different thresholds than the defaults. Once you apply it, you can see that there's an additional sample that's being caught and being marked as out of bounds. Let's change this back to the defaults. Okay, so we have two out of bounds samples out of a total of 41 samples processed. So QC call rate will almost always be the same as call rate if you're not adjusting the analysis configuration. Call rate is the fraction of genotypes within the sample that have returned a clear genotype as opposed to a no call. So basically there's call rate, there's PRA count, which is the number of possible rare alleles that were found for the sample. Now it's a possible rare allele. It could just be inaccurately called data point, but it could be real rare allele. Number of SNP markers that are being genotyped. This is whenever you're using the consented marker list DMET plus all, this will be 1931. If you choose, when you register your samples in Command Console, to use a different consented marker list, for example, DMET plus validated by Affy 2009, which is a subset of the 1931 markers, you'll get a probe set count that's somewhat lower. And then the call rate that you get will be based on that. So if you use a restricted marker list, then the genotype results files, the CHIP files, will not store the signals or the genotypes from the markers that you did not consent to have genotyped. And so the probe set count will go down, and the call rate will be a function of how many probe sets you decided to try to genotype. A calculated column, computed gender, and then from the sample files that are associated with the CHIP files, what sample type is it and what is the consented marker list that was used. So these are the general metrics for this. You can access more metrics by going to the all columns view. You can visualize this data a number of ways. One is you could, for example, sort on QC call rate in ascending order to find the samples that how many samples failed QC. If you, I guess, scroll to the middle of this window, you could say what the median call rate is across this data set. You could also do a visualization, a line graph, which is available for some tables that have numbers in them. So if I click on this, the default is to put each sample on the x-axis and the first metric that it finds, in this case QC call rate, on the y-axis. So we have 2 outlier samples, and then the rest have good call rates. You can adjust axis limits or change what you want displayed on the x-axis and change what metrics you want to show on the y-axis as well. In addition to that, you can export the data or the image. Let's close this line graph. Okay, now that we've reviewed the general sample statistics and notice that there's 2 outlier samples, let's see if the assay might have had another problem. Let's look at the statistics from a marker level. So we have 3 genotype results groups, all, which basically refers to all the chip files in this data set. We have one that's filtered to just only the chip files that are passing, that are inbounds. Or if you wanted to just jump to the samples that were out of bounds, you could click on those. For example, I could say show chip summary, and it would create a table that only shows the failing ones. Let's only look at the samples that pass QC. So this is 39 samples. Another view that we have on looking at just the inbounds one is show marker summary. And we can select what set of markers we want to see a summary on. Right now we have our 3 predefined lists, and let's just look at all markers. It starts by auto scaling. Let me turn off auto scale. So the marker plot has 2 panes. The top pane is a cluster plot, contrast space versus strength space. Let me adjust one more thing here. X-axis limits, I like to have it centered at 0. Let's say -7 to 7. So each of these data points represents a sample. Right now, the abstract allele code, genotype call AA, refers to that we're homozygous for the allele A. For this particular marker, allele A has the C genotype. So basically, everything that's red is CC. We also have the second allele for this genotype, G, because this is a SNP that changes from C to G. And we don't have any GG homozygotes or CG heterozygotes. We color code the shapes of the labels will change depending on what sample type it is. If we want to look at only samples, we see that. If we want to look at only controls, we'll get the data points with a little C icon around them, so we can see if the controls are behaving any differently than the samples. You can select which marker you want to look at via the table below. So right now we've got this cursor is on row 1, probe set 10,001, and this marker is selected. If I use the down arrow or click on another marker, I can scroll through the performance of those markers across all the samples in this data set. Summary statistics for the marker in this table. There's the marker call rate in the set of samples. Now, since I've already filtered it down to just samples that pass QC, the marker call rate can be up to 100% frequently. I've chosen to only look at passing samples so that when I find outlier data points, I won't be fooled by it possibly being due to a suspect sample that has low call rate. In addition, we have the possible rare allele count, which for these markers is all 0 because we're not seeing the possible rare allele genotype showing up. And actually, we can try to find some of those. So I clicked on this column, sort in descending order. Say which markers have the most possible rare alleles. This first one has 4 possible rare alleles. They turn out to be all controls. And then for the rest of them, we can see that we have major home, a het, and possibly a minor allele. Possible rare alleles are called when in the training set that was used to define cluster boundaries, the minor allele was detected so rarely that we did not have a high level of confidence as to exactly where the cluster, the genotype location was. So at this point, we're just calling it as a questionable call, and that it may be a rare allele that you should follow up on, but can't be sure. After the possible rare allele, let's resort here and go back to the first row. We have minor allele frequency. That's fairly straightforward. How often does the minor allele occur relative to the major allele? What are the alleles on the reported strand? What is the relative frequency of those two alleles? Actually, we have 3 frequencies listed because this panel also includes triallelic markers. Let's find markers that have 3 alleles. So there's a number of markers that have 3 alleles. Depending on your data set, you may not see all 3 alleles represented. Following this, we have basic information on the chromosome, where it's located, its RSID, and one that I wanted to get to, which is the MPCR region. So there are certain regions on the chromosome that we do multiplex PCR on to amplify certain regions. And the purpose of this is to make sure that when we genotype regions that have similar sequence homology to other regions on the genome, we only want to genotype a particular location on the genome. So what we do is preferentially amplify that region to make sure that the assay will preferentially measure that region. So the reason this is pointed out is that this is a step that could be forgotten in the assay to re-add the MPCR material back into the genomic prior to performing the rest of the assay. And you can tell that there's a problem if when the call rates for markers that belong to MPCR regions is substantially different from the call rates of markers that don't belong to MPCR regions. So one of the QC checks you should do if you suspect that there's a problem is to look at the markers in MPCR regions and see if the range of call rates for those markers is substantially lower than the markers that are not in MPCR regions. If you don't notice that, then you don't have a problem and you can continue on. You can use the marker summary window to do a number of other things. For example, you can take the data that was used to generate these plots and save that data to a file in case you want to use another tool to look at the data. There's another way of getting these results. You can save screenshots of every one of the markers that are in this table to a PDF file. It will save 8 marker plots per page. Or you could just save this one particular image to a file or copy to the clipboard. That's what you can do with the top pane. And the bottom pane in the table, you can change what set of fields you want to see and in what order using the first 3 things. You can, again, as with all other tables, use the general features of copying either the entire table or certain rows to a clipboard, saving it to a file, looking for information, or sorting on metrics of interest. I like to use this table as well to create custom marker lists. For example, let's say I was only interested in one particular gene. What I could do is, let's say, sort on column name. Let's say I only want to look at VCore markers. Scroll down. So let me select all the rows that have VCore. I'm going to copy to the clipboard. Paste it into Notepad. Save the file as, let's say, VCore. Now, in marker lists, I'll right-click and say Import Marker List. Find VCore. What name do I want it to show up in here? Let's just call it VCore. And here we go. So, I I can do a number of things with that marker list. One of the things I can do with it is reopen this marker summary, and this time select the VCore C1 marker list. And now I only have 22 rows. So I could create a PDF that has only those markers, or summary statistics that have only those markers. I could do a number of other things with this as well. The only field that is red when you load in a text file is the probe set ID field. So it didn't matter that I included other fields in here. So you could create your other list this way. It just has to start with probe space set space ID. Okay, so I've viewed some basic results. What else can I do with the genotype results that were generated? Well, I could look at the copy number summary. We do copy number analysis for 5 genes of interest. Let me adjust the scale here. So for CYP2A6, all the samples had a copy number of greater than or equal to 1. Same for 2D6. For GSTM1, we had a set of samples that had copy numbers of 0. This is not uncommon for GSTM1 or GSTT1, where you have a double deletion of the entire gene. Another thing you can do is export genotype results. Get your data out. Export file name. Let's call it AU fixed v2. We have a number of different formats for saving the results. A popular one is to collate the results across all samples. Let's just see what that looks like. Let's only look at the genotype results for now. And let's actually use the marker list again. Let's only look at the VCore C1. There we go. Let's open it up in Notepad. Fairly straightforward. Each column is the sample name. Each row is the marker. Right now we just have the probe set ID. You can join that up with the DMET plus all table, which links the probe set IDs to any information of interest. So you can use Excel or another program to join that information. And in terms of the sample names, if you're not happy with the names of the chip files, you could always dump out this table that says for each chip file name what is a particular attribute of interest. For example, you may have an attribute that allows you to include the individual as the name. DMET Console allows you to compare your genotype results against that of reference data to see just how concordant it is. To do this, select a set of chip files and perform the Run Concordance Check operation. The left pane is a list of chip files that are available for doing concordance against, along with one of the chosen attributes for each of the chip files, which is pulled from the sample file. If you don't show an attribute of an individual's DNA, you might have to select a different one. So let me sort here and select 4 replicate samples of NA 12003. I'll add 3 of them to the test set and compare each of these 3 to the same 4th replicate, just as an example. In the right pane, you have each row is a pair of chip files that are being compared, test 11 versus test 9 in the first row. If both chip files have sample attribute files, it will show the test attributes for each pair, and if they match, the status will say match. This will help you identify any mismatched samples. There's another way to select reference data, for example, if it's not in the current data set, but in this case it has to be a text file. So let's take a different sample that we have. Let's add a set of samples at once. For reference data, one option you have is to use the reference genotype supplied by Affymetrix. Just go to the DMET Console software page, and under technical documentation you'll see reference data available. So I downloaded that zip file, unzipped it, and in this folder we have information from 3 different plates. A controls plate which has 6 genomic controls. I believe 4 to 6 are currently being used. However, I want to compare it against samples from the accuracy plate. There's a lot of samples here. They include the core allele name. A quick way of selecting just the samples you want is to filter on part of the file name. So you can use Windows Explorer and use the star wildcard character to say find all files that contain the 188 string in them. So let's open that, and Windows will just return a list of files containing that. Let's select to add all of these, and they're added into the right side. Let me readjust these with a double click. Okay. Because these reference text files don't have a sample file from which we can pull the reference attribute, we can't use this matching feature to detect whether the samples are paired up properly, so we'll have to look at the file names. For example, we can see that this first one, NA 18855, does not match with this one. So what we're going to do is we're going to move the one that does match on the right half of this table up 1 row, and now this 18855 matches with the left hand side. So as we scroll down, we see if there's any other mismatches. Here there's another one. The 63 sample needs to go down too. And as it goes down, it swaps places with the one in a different row. So now we have all the samples paired up properly. We have the same number of test files as reference files, which then allows you to enable the OK button. So let's perform a concordance check. It'll ask where you want to save the report. I like to put it in the same folder that the chip files came from. You can change the name of the concordance report. When it's created, it'll be saved in the current data set from which you can review at any time. 2 windows are open, a sample concordance and a marker concordance. Let's look at the sample concordance first. 10 pairs of samples were compared. The first 3 were 3 chips in one data set to 1 chip in the same data set. And you can see that although the second 2 have 100% concordance, this first one, test 11, is not 100% concordant with test 09. How does this calculation come from? Well, it's based on the number of markers compared, which is only comparing the subset of markers that have a call for both samples. So no calls are ignored. And for pairs of samples where both markers have calls, how many agreements were there? So number of agreements divided by number of markers compared. And one thing you can notice is that the number of markers compared in this row is a lot lower than the other ones, indicating that there's a problem with more no calls for this test 11 sample. But we can come back to this. We have one other sample that seems to have issues. Either the accuracy reference data has an error or test 17 has an error. We can also look at this on a per marker basis. Because we have 10 pairs of files compared, we can have up to 10 comparisons for each marker. And how many times did those genotypes agree? Gets you number of agreements, and concordance is based on that. Let me just sort on markers in increasing order to find the 6 markers that have less than 100% concordance. We can look at these in a cluster plot to learn more about the performance of these markers. So I'll select these rows, copy them to the clipboard, paste the clipboard into a text editor like Notepad, and I'll save this to a file I'll call markers of interest. I'll add this marker list to my workspace, keeping the same name and associating with the DMET plus array. And then I have it. With that, I can now go to Show Marker Summary, select to look at only these markers of interest, and I'll have 6 markers only selected. The first one that's shown is showing the corresponding cluster plots here. And what I'm looking for are data points, each of which corresponds to a sample that might be outliers. And I can tell from this that there are 2 data points that are color-coded as heterozygous blue, but look like they're closer to being the homozygous BB call. If I click on each of these data points, I'll see that one of them belongs to test 17 and test 11, which was the 2 samples that were identified as possibly having issues when I looked at the sample concordance tab, test 11, test 17, both of which had a smaller number of agreements and comparisons. Finally, let me look at the genotype results, show the CHIP summary table. There are 2 outlier samples. They're both considered out of bounds. It is test 11 and test 17. So these samples would have failed QC, and in fact did. And this is actually why failed samples should not be used for concordance check, because they're the ones more likely to have errors. So when you do a concordance check, it's recommended that you use the inbounds data group.